Hi, this is Karl Freund of Cambrian-AI Research.
And Jim McGregor from Tirias Research.
And we're here to chat with Nandan Nayampally, the Chief Commercial Officer of Baya Systems. Welcome, Nandan.
Hey, thanks, Karl. Thanks, Jim. Good to be here.
Yeah, good to see you again. Good to see you again. So what we'd like to do is just introduce Baya Systems to the audience and talk a little bit about the why. Why are you guys doing what you're doing, and what are you doing, and how do you differentiate in the marketplace? So let's just get this train going, okay?
Great.
Let's just start with the big challenges in AI today, Nandan. Where are we in the AI development cycle, and what's preventing us from reaching that next phase of development?
That's a great question, right? So if I look at AI in general, it's been obviously decades and decades leading up to it, but the last 15 years have been probably a steep growth curve, right? So if you look at the last decade, let's say 2010 to 2020, it was predominantly driven by CPU, AI driven on CPU, which was adding in basic sensors and perception. As models, especially deep learning, took off and GPUs started becoming much more applicable, I think the application started growing, the actual depth of understanding of AI started growing. And so we're now in the generative AI space. And that, I think, is also driving even more take up. And as we go into the next phase, which will probably more be on the cognitive side, it'll continue to burgeon the main challenges that I think Baya Systems is trying to address. Of course, Baya Systems is a small startup in the bigger ecosystem. Finally, AI is about data and understanding of that data, converting that into information and better understanding. So what we've seen consistently is the move from traditional compute mindset to a data movement mindset, a data understanding mindset. And that's exactly what Baya is focusing on. How do we actually make the efficiency of data movement between widgets to and from memory that enable AI to scale faster?
So why are these hardware issues just popping up now? We've had AI kind of in full bore since ChatGPT. So why are we having this conversation? What's going on? What are the limitations of traditional architectures?
So if you think about CPUs in general, right? So CPUs were much more control flow architectures, which are great for programmatic models. But AI and most thinking is much more wider. You talk about wider data. It's not as programmatic. If you think about how GPUs then started looking very wide matrix multiplies, which they are better suited to do, they started doing that. But you also see the industry beginning to pick up on different architectures that make neural networks and kind of foundational models. All these models work better. You need different types of compute. So you will need procedural capabilities and CPU capabilities at some part. You need wide data movement and data capabilities, matrix multiplication, GPU style, accelerator style capabilities, but it's not one or the other. It's all of the above working in unison. And when they have to work together in unison, the challenges in how data moves from one to the other, how do you maximize the usage, minimize the amount of movement if possible. And what we're seeing, especially with the pickup of ChatGPT, generative AI, is that the scale is increasing rapidly, right? So firstly, the size of the models are growing. You have to do that closer together, otherwise the response times and the actual communication start becoming severe bottlenecks. If you start doing, and that's kind of what you're seeing today with scale up. I mean, NVIDIA has done a spectacular job of understanding ahead of time proactively that it was going to be limited by data movement and connectivity. So the Mellanox acquisition that led to NVLink and NVSwitch showed it, right? There are advantages there. And then, of course, as you start doing more and more things in parallel, you're going to do scale out, which means a lot more models running in parallel, because there are a lot more services that you have to support in parallel. So really what we're seeing right now is the scale is exploding. And that's why the general challenge is, how do we actually make that more efficient? You've seen companies like Fabrica that we're talking about how we do scale-up switching in a more efficient fashion. You're seeing a lot more focus now on connectivity, communication, and data movement being the real bottleneck that needs to be solved for AI.
Nandan, I completely agree with you. Matter of fact, just our forecast showed that we're going from like 667 trillion tokens in 2024 to over 80,000 trillion tokens just for those text and audio tokens. And when you add in multimedia and everything else, it's probably going to be about 4 times higher. And it's interesting because at Intel's Direct Connect in 2024, Pat Gelsinger talked about, how we have to have a densification of compute. How do we bring all these resources? You're right. NVIDIA's done a great job of scaling up to, 72 and pretty soon to 144 GPUs into a single rack. And that single rack is a single computer. But, Pat talked about, we need to put everything closer together. We have to have those CPUs, those GPUs, the memory, the networking, all into a single module. And it was kind of interesting because he was thinking 5 kilowatts. I'm talking to people and they're saying, oh, it's going to be 30 kilowatts. So how do we do that densification? How do we get everything into, I guess that's one of the biggest challenges, not just scaling up, but scaling at a modular level. How do we do that?
I think you use the word densification, which is really, I think, gets to the heart of it, right? And we've worked together for a while now in my various roles, you continuing to be on the business of understanding and projecting. And I see, if you look back at 15 years ago, you looked at how SoCs, especially in the smartphone world, started combining all the key components onto the same die, like more advanced systems on chip. As you've seen the transition from especially how data centers are moving, you have to right-size compute, right-size communication, and right-size memory to kind of fit those purposes, because that's the only way you can get the densification you need. If everything becomes discrete and separate, it's very tough to get what you're looking for, which is best-in-class density for what you're trying to achieve. So what we see is clearly you need to start getting the complexity of these heterogeneous compute engines, if you will, that need to work much closer together, because that's where you get very efficient compute at the subnodes. And then you need to find a way to make those things scale in an efficient fashion as well. So one of the key technologies that has emerged very strongly over the last decade or so lends itself to this effectively a modular approach that we need to build, which is chiplets. Right? So you saw the transition, especially for companies like AMD, using components that are built right-sized and then potentially scaled together in different packaging setups that meet the right performance levels, but there's a consistent densification. And what we're trying to do is very similar. We're trying to find efficient ways of connecting these widgets on the same die. And as data movement becomes the primary issue, as the number of wires and logic that's connecting all these things becomes more kind of the bottleneck, we need to find ways of how we do that more efficiently. And that's how Baya is kind of focused on getting common transport that can connect different types of protocols on the same transport, making it more efficient, combine where needed, or redundancy and parallelism where needed to get exactly what you need for those types of use cases. And then you think about, actually, when I look at my system, I can, as I try to build bigger chips, you start running into cost challenges, right? So you run into reticle limits, yield issues, etc. If you start putting them all closer together on the same die, it'd be great. Somebody like Cerebrus does a vapor scale processor, which is effectively another way of densification, but has its own challenges and economic impacts. So chiplets become a very good way to achieve some of that efficiency in densification, and at the same time allowing for scale. Does that kind of resonate with what you've seen in the market?
That does. But the biggest challenge, and you brought this up, was the fact that you have different protocols, different interconnects, whether it's memory, whether it's an accelerator, whether it's whatever. So, I mean, and that's probably the most interesting thing I find about what Baya is doing, is trying to create that common interconnect, or the common layer that's going to allow all these different things to actually interconnect simultaneously and at very, very high speeds.
Yeah, and in fact, if I look at the market itself, it seems like it's ready to explode, right? So the general idea was silicon design is at least $1 trillion in terms of revenue for the whole space in the next 3 to 4 years, out of which more than half of it is likely to be AI and specialized AI solutions. That's a huge market. That's a huge spend. Obviously, there are technologies that need to go address it, but still there are key challenges, right? How do you understand now the complexity of these kind of burgeoning systems? How do you know that they are actually going to deliver the performance on the types of workloads which are constantly changing, as you know, right? Hey, you had deep neural networks, you move to kind of LLM foundational models, you're seeing different types of state space models, et cetera, coming in. So you have to have platforms that are both efficient and designed for purpose. At the same time, they need to be versatile to be able to move with the changes in the AI kind of software stack space. So how do you do that? How do you actually make every chiplet, every SoC more efficient? And then what's certainly happening is things need to move much, much faster. So the time to market for a lot of the designers becomes critical, because the market windows are small, especially with giants like NVIDIA, Broadcom, all serving these markets. There are limited windows, especially for small and mid-sized companies, to make their kind of products hit at the sweet spot that they need. So those are all challenges that need to be solved, and that's kind of what we were hoping to do, and that's what we have been doing over the last 2.5 years. For those that haven't quite heard about Baya Systems, it's only 2.5 years as a company, but we have, over the last year, kind of gone through a lot of traction, because every piece of the challenges that I just mentioned and the challenges we try to solve are actually resonant, and the product is actually validating itself in the market.
So you've got basically a protocol agnostic transport layer that you're applying both chiplet to chiplet and off chip, right? How big is that market? What do you think your total addressable market is, or serviceable market?
That's a fair question. And in fact, this is, I think, interconnects in general, and especially network on chip interconnects, are beginning to come into focus, right? So off chip certainly has had a lot of work, and especially as you look at optical networks and even silicon-based photonics, kind of extending it outside of chip or chiplet. On die is probably the fastest growing subset in that regard. I mean, today it's not very big. If you purely look at the IP portion of it, it's probably a total addressable market that's a little over $1 billion, $1.5 billion. And majority of that, if 75 to 80% of that is in-house designers, because you're doing very custom fabrics, networks on chip to fit your specific needs. But as these designs get more and more complex, the cost of doing, maintaining, and still being best in class becomes more difficult. Projections that we've seen from some of our research and partnerships project that within the next 3 to 5 years, that market will probably quadruple, right? So $4.5 billion in terms of network on chip IP and related kind of software that is needed. So it's a pretty fast growing market. Still, there will be a lot of investment in the medium to big size companies that's trying to do this in-house. But what we're seeing is still the cost of trying to develop that versus what we can provide because of our modular approach, because of our ability to scale on a common transport to different types of protocols and have that flexibility to change the design at any point in time, kind of places us very well for that market. Just to give you an idea, we have a software and IP kind of portfolio. Everything from kind of understanding at the top of the architectures, like, hey, how do I design my system, if you will? How do I partition my memory? How do I partition my processors across a single die, multiple die, down to building the microarchitectures for each of those chips or chiplets, and then also post-silicon tuning. It's a very common flow that connects across. You can run workloads that you're trying to get to all throughout that system development. And then, of course, you're building with the software-driven approach, a very, very quick turnaround time design of your system that enables the rest of the system to kind of work together, right? All the widgets that are usually the more complex things that you need to design independently, but usually system is always done last, whereas here, you get right from the start, you have a system that's in place that supports all the other compute elements to work together really well.
So I have to ask you two natural questions. A, where are we in validating this Baya approach? And B, how far can it scale?
That's an excellent question. So I think what we've seen, again, this probably goes back to reminding the listeners as to Baya, you may not have heard of them. The founders of Baya, like Dr. Shailesh Kumar, Eric Norridge, Joji Philip, came out of a startup called NetSpeed that started about a little bit over a decade ago, got acquired by Intel. The team worked in the Xeon space for a little bit and then effectively stepped out to start this again. So this is effectively a third generation of architecture development. I would argue almost the religion has been on software-driven techniques to build out networks, right? And what we see thereafter is, if we go down that path, the scale is, it's always limited by a number of what your reticle limits can support. But again, if you build it within chiplets, you can scale beyond that. So our software and the architecture doesn't really have limitations of scale. The scales are going to be based on process technology limitations or other limitations that may come up. For example, we recently launched a very innovative and potentially radical way to enable the new emerging scale-up market. We are actually a product called NeuraScale, which does effectively replaces the need for a traditional crossbar, but it's based on a very easy modular network on chip or mesh type solution, but provides all the characteristics that you would expect from a crossbar, being non-blocking, guaranteed latencies, and the like. Today, if you look at NVIDIA's NVSwitch, it's like 72 port solutions today. And if you look at Broadcom's Tomahawk switches, Tomahawk 5 was 50 terabits per second. I think Tomahawk 6 is probably double that coming in. We can demonstrate how the NeuraScale switching on a single die in a very small portion of that reticle can hit 256 terabits per second. And because it's designed in a much more simple digital format that can be fit into standard SoCs, it allows for enough shoreline on the SoCs so you can actually do multi-chiplet solutions which can scale much further. So 144, 288 ports would be viable soon based on what our partners will take it to market with. So the scale itself is pretty broad and actually going to be defined by the customers. But that's actually why we're seeing the traction that we're seeing. We have 10 plus design wins, both in our traditional fabric, which is on chip processing, heterogeneous processing, as well as some of the emerging markets like scale up, where we're seeing a lot of interest in our approach.
So obviously the AI market's growing dramatically, and the size of the systems are growing even more dramatically. And you talk about scaling within the chip. What about scaling out and scaling up? I'm in particular interested in your perspective on NVLink Fusion and how you play with that or versus that. Kind of position that for us, please.
Yeah, sure. So clearly, I think your article on scale within, scale up, scale out probably gave a pretty good outline for people to understand the differences. You're right in that traditionally what we're talking about as a network on chip is really a scale within. Scale up is kind of connecting as many closely coupled processors as possible to handle a model and a larger model, whereas scale out is having a lot of parallel models running. So each has a different type of scale. So when I refer to scale up, we are actually trying to be the switch component that will go into broader scale up racks or solutions. So this is where NVLink, as you mentioned, has already pioneered that path. You're seeing emerging standards like UA-Link come in, which are broader ecosystem supported, and you have similar ones like Ultra Ethernet coming in, which may support both scale up and scale out. So what NVIDIA has done really well is enabling that scale up capability with NVLink. And with Fusion, they're actually opening that up to other partners that can closely couple their solutions to the compute cluster that is built around NVIDIA. Right? And that's certainly a very strong market. What Baya does and what NeuraScale provides is IP that can enable such switching solutions. Obviously, you're not going to see that in NVLink because NVIDIA has an extremely well-developed solution for it. But other players in the market that may be trying to build their switching to match up with it, or build their switching to match up with UA-Link or Ultra Ethernet UEC, can use our technology to get to market a lot faster. And one of the key elements of that is not only is it easy to kind of understand and design with, integrate, because it is much more digital and modular, it allows for a very tiled implementation approach. As you start looking at switches and very high performance switches, crossbars, you need a lot more physical implementation resource. You have tens of engineers, if not more, to kind of go build that out to the specs that it needs. Whereas because we can take a very modular approach, more standard tool flows allow us and our customers to build this out much quicker and to spec.
Yeah, so that time to market is really critical, I'm sure, for all of your customers.
Indeed, and basically it's the cost of development, the cost of silicon, of course, the cost of implementation, and the most risky cost of time.
This is amazing because you're basically getting rid of some of the barriers that we've had to actually being able to do that densification. I think the bigger challenge now is how do we cool it and how do we power it? But I'm sure we'll get over those challenges too. I love what Baya is doing. You're basically enabling the entire ecosystem to build these heterogeneous solutions to really have this densification. I guess the only question is what else are we lacking? I mean, I know you guys are working on the tools, the software, the hardware, the physical layers and everything else that go inside. Is there anything else that we have to have before we can actually do this?
So from our standpoint, right, so I'll kind of touch on the elements. If I look at actually building designs, right, I think we have addressed a lot of the key problems with how we do our front-end analysis, exploration, how we can actually enable partners to do all of that design. And we've demonstrated it as well. So you've probably seen the announcement with Tenstorrent about 2 weeks ago when they launched their Ascalon processors, IP that is. And then we demonstrated how very quickly we could come up with a very efficient, almost compute subsystem with our IP that supports coherent, it supports non-coherent, it supports even AI custom fabric that can be pulled together. And all of that with a reduction in footprint, in power compared to the prior generation products that they had. They did a similar analysis with AI, with fabric, because again, AI engines are very interesting, but it's all about how efficiently data moves between them. And we could demonstrate, compared to prior generations, like a 60% increase in the efficiency in the system while taking only half the footprint, like for like, right? So I think from that standpoint, we're really there. The tooling that we see is enabling chiplet development, I think, but the big, I think, scale will come in when you can actually combine best-in-class chiplets, let's say, from different merchant providers, rather than each system having to be built by, of multiple chiplets having to be built by the same team or the same company, right? And if you want to look at that environment, I think the technologies are there. They're reaching to some level of maturity, but I think there are probably some of the business challenges that will have to be addressed about how, when you're combining chiplets from best-in-class different vendors, how the liability is set up. But these are all things that are who underwrites some of the challenges there. But this is certainly within their realm of various foundries, packaging companies that can actually build with it. So chiplets today, I think everybody's beginning to take a step towards it, especially in the automotive sector, in the data center sectors. Clearly the margins and the value defines it. But if we want that to go broader and truly scale, because from my perspective, AI is not just data center, AI is end to end, because finally the sensors, the data input points are as important as the data manipulation or data understanding points. So if we have to get to the next level of AI, which is cognitive and beyond, all of this has to work much more closely together, which will require right size solutions from the very low power sensor all the way up to the data center.
So chiplets have a tremendous opportunity that we've all been excited about, but yet I haven't really seen chiplet companies that are selling chiplets, maybe Tenstorrent's an exception. What's stopping that? Is it governance that's maybe a barrier to chiplet adoption from combining multiple chiplets from different vendors and then putting those into operation? Is that the challenge? And if so, how do you envision the industry addressing that?
Fair question. I think there are two or three things that you will see that are kind of basic and fundamental. Certainly interoperability, right? So there are lots of standards like UCIe that allow for interchiplet communication, but not every component available in the market is fully interoperable. So there are some more technical challenges or basic challenges that need to be solved about how these components interoperate. Then if you move up a level beyond that, verification of the entire system, especially things that may have been designed independently of each other but need to work together, also has a broader, kind of bigger challenge that needs to be solved, unless you're thinking top down from how the system needs to work, and you design each component with that thought. That's somewhat easier. If you're buying off-the-shelf components, then that kind of adds a challenge, which is still, I think, in the process of being solved. And then, of course, the third challenge that I mentioned earlier, which is if something goes wrong, who takes the hit when you combine chiplets from different vendors that have to work together, right? So there's a base technical challenge, there's a system level understanding, performance, and verification challenge, and then there is a economic challenge on underwriting, let's put it that way. I think those are the three things I can think of. There are lots of players that are beginning to play in this space. Clearly, Tenstorrent is playing in that space, though more likely than not, they'll be designing products that are very specific and probably working closely together with their own. Along with some key partners, you're hearing things like what ARM may be doing in that space, enabling chiplet, and that's why they have both come up with standards that'll enable the ecosystem. So the chiplet specification or architecture from ARM, the OpenChip Atlas architecture from Tenstorrent for the RISC-V market. So you are beginning to see the ecosystem enablement happen. And once the broader ecosystem starts supporting it, I think there is a better chance of this all coming together.
Sounds exciting. Sounds exciting. Well, we're definitely in an interesting point, and perhaps an inflection point of AI taking over so much of the work that's being done with procedural languages and computers that it's just fascinating to watch, and watching the technology that you're providing really enable that scale to happen in an open environment.
Indeed. And in fact, for me, my analogy, which may be trite and may not be perfectly on point, is I think from an AI perspective, we're probably like in the late 90s in the internet revolution, where we thought we could do so much with dial-up, right? It needed broadband to be kind of fully prevalent, and it took off. So if you consider that as an analogy, and again, data movement, connectivity is going to be a critical piece that really takes this off to the next level.
Yeah.
So you're basically solving the data layer problem.
And very layered parts of data layer, yes.
Fascinating.
Well, that's great.
I think that it's great. We really appreciate your time, Nandan. It's been fascinating, and will be even more fascinating watch how Baya evolves in the marketplace.
Thank you so much. Thank you for having me on. Thanks, Jim. Thanks, Karl.
Thank you.
Thank you very much. Take care. Good luck.